Hi, listener. This is From Ideology to Unity, a spiritual journey where we let go of ego and ideological doctrine in favor of meaning, purpose, and unity as a whole. Right, so today I'm doing another reading of Quantum Theory and Free Will, How Mental Intentions Translate into Bodily Actions by Henry P. Stapp. So, now we're at the beginning of chapter 5. The physical effectiveness of conscious intent. Actually, let's just quickly check, where were we last time? Right. So we're dealing with the problem of how whatever, I'll just get on with it. Well, it's dealing with the holism, the pantheistic aspect. It's starting to get more into that sort of thing, which is interesting. And we may well get more of that. Right, so chapter 5, the physical effectiveness of conscious intent. A brief review. Classical mechanics says that your thoughts cannot affect the behavior of particles, but realistically construed orthodox quantum mechanics says they can. The original Copenhagen quantum theory was designed by its founders merely to reliably predict relationships between what we do, the experiments that we perform, and the outcomes that we observe. Then, even at this initial stage of quantum mechanics, we observers do not just passively witness, we also passively act. We choose on the basis of our personal values what our atom-built brains and bodies will do. These actions are often tied to our imaginary perceptions of perceived events that might occur out there and in the future. But when formalized by the work of von Neumann, the theory produces a dynamical conception of reality that can automatically explain, without any change in the dynamic rules, not only the statistical relationships between our probing actions and our resulting perceptions, but also the capacity of a person's mental intentions to influence that person's bodily actions in the way that he or she mentally intends. And this is key because that simple thing goes beyond what is predicted by the, I guess you could say, physicalist paradigm, in which everything mental cognitive is entirely a reflection of physical. That is a significant development, an automatic explanation of how a person's free-willed intentional mental effort can influence in the intended way that person's bodily actions. Quantum mechanical dynamics thus joins together with what classical mechanics has rent asunder, our minds and our bodies. So this Descartesian dualism, I suppose you could say, or this division anyway between mind and body, and whether you put the mind in charge or the body in charge. Well, I mean, splitting them apart like that, certainly, yeah, it's no longer, it's brought into disrepute by, there's something unifying about realistically interpreted orthodox quantum mechanics. According to the standard quantum principles, our choices of which probing actions to perform and when to perform them are not determined by any quantum mechanical law. I mean, that's pretty significant, right? These choices enter the theory as free, uncoerced by material causes choices. And a suitable structuring of those free choices can tend to make your physical body move in accord to your mental intent. So actions, primarily of people, is a huge part of, well, that's It's a very significant thing. It's observed a lot. A lot of stuff. People do a lot of stuff intentionally, and mentally, and then acting on that, based on free choices. And the theory establishes that there's a fundamental aspect of this that isn't based on, can't be explained with just the physical manifestations, because of how process one seems to choose which outcomes play out. And then from there, the Schrodinger equation sort of makes it play out, or operates it, right? Like sort of like coding. But which, it's like there's a bunch of different programs that can play out, but we pick which one. Or better computing, in a sense, that you pick which software to use or something. Or anyway, so it's like, yeah, the free will aspect of things. How can this come about? How can something as intangible as a mental intention cause physical objects such as your arms and legs to move in intended ways? By what process can the motions of your fingers come to express the complex thoughts that you intend to express in written words? Or, when you're gesticulating, when you're talking, there's very much, often there's a physical aspect of it. The Quantum Zeno Effect. Within the orthodox quantum mechanical description of nature, this physical power of your conscious thoughts can arise from a well-known rigorous property of quantum mechanics known as the Quantum Zeno Effect, and sometimes as the anti-quantum Zeno Effect. Suppose a physical material system is being probed by an observer whose mental aspect, his ego, is free to choose a sequence of probing yes-no questions that will elicit responses, yes or no, from nature. And suppose this ego would like the observed system, originally observed to be in a state phi 0, to move from that state to a perceived final state. Yeah, honestly, this is mathematical notation, and I'm going to just butcher it. And you're just going to have to deal with that, I guess. Okay, so to be in a state phi 0, to move from that state to a perceived final state, that looks like a P symbol, but with a shortened, but kind of shortened. So P bracket 1, close bracket, along a smooth path. I'm tempted just to skip that. Like, I imagine the listener doesn't know the maths involved. So, okay, so I'll start again. Let's see if I can. And suppose this ego would like the observed system originally observed to be in state, say X, to move from that state to a perceived final state, Y, along, it doesn't say X and Y, but I'm just going to say that for simplicity, along a smooth path as it changes from one state to another. Then the quantum mechanical laws of motion entail that if the ego chooses to pose at each time, at given time in the set of rules, the question, do I perceive the observed system to be in the state X, then the probability that in all n responses of nature will be yes tends to unity, i.e. 1, as n tends to infinity. All of nature's responses will, by virtue of the Bohr rule, almost surely be yes if n is sufficiently large. N being number, I suppose. Thus, by suitably rapid choice of probing questions, the observer can, by its choices of these questions, effectively control both the perceived responses and the associated material reality that is being perceived. So what on earth is that? I guess what it seems to be saying is if the ego, so the observer's mental aspect, the observer's mind, would like the observed system to change to a perceived final state. So there's a set of probing that's done. This is a process one. It's essentially through process one, there's a series of yes, no answers, yes, no questions that are all done in an instant, effectively. And based on that, observation interacts with reality in a quantum way. And through the answers of each of those, what you get is an effect from the observer onto the observed reality. And it's essentially a choosing which process two outcomes to play out. And so the question, do I perceive the observed system to be in a certain state, basically, then the probability that all responses of nature will be yes tends to unity. So no tends to be disunity and yes tends to be unity, I would say. Yes is acceptance, no is rejection on a fundamental basis. And acceptance is required for opening of the heart. So that just, and that higher, those high frequencies, that just seems to translate to me anyway. So, and as it says, thus by suitably rapid choice of probing questions, the observer can, by its choices of these questions, effectively control both the perceived responses and the associated material reality that is being perceived. Now, does that sound like the law of attraction to you? It does to me. Anyway, because the observer's choices are stemming from the mental realm, there was no known limit on exactly how rapid these free choices can be. But it is reasonable to suppose that survival consideration makes this effect far easier to use if the action is directly an action on the observer's / actor's sensitive brain than on a perceived brute external system. Thus, the behavior of the brain, according to orthodox quantum mechanics, is not completely determined by prior physically described properties of the universe alone, but can be significantly influenced by free choices made by human observers pertaining to which probing action to instigate and when to do so. Here again, the free in free choice means specifically that this choice is not determined by the prior physically described aspects of the universe alone. Well, that would be determinism. It's not our determinism. Our conscious free choices and mental efforts enter naturally, according to the quantum mechanical dynamical laws, into the evolution of the psychophysical universe. I shall describe next how, within orthodox quantum mechanics, the simple holding in place action produced by the Quantum Zeno Effect can tend to make a person's physical actions conform to that person's mental intent. Templates for action. Suppose, for example, that you're struggling unsuccessfully to put a heavy object onto a truck in order to make needed home improvements. Suppose you are mentally wrestling with whether to try harder, get help, or give up. It is reasonable to suppose that in this situation, your brain will construct via biophysical processes and on the basis of previously learned habits and responses, several different patterns of neurological activity, each which would, if held in place for a sufficiently long period, while the other patterns are suppressed, send out a sequence of neural impulses that would cause your body to behave in one of the possible ways responsive to your plight. If such a neural pattern is called a template for action. Sounds like a sort of sequence of programming. Mutually inconsistent with a number of others. Seems like a superposition or quantum theory situation to me. So this situation can be analyzed within either orthodox QM or classical mechanics. If one uses classical mechanics, then the fact that in classical mechanics our minds enter only as passive observers means that that theory can give no dynamical explanation of the connections between, on one hand, your feeling of making a mental choice effort to actualize some intended bodily actions, and on the other hand, the associated responding movements of your physical body. For your mind is required to be causally inert, not part of the dynamics. But why should one's mind exist if not logically entailed by the classical material activity and has no function? Why should it delude us? Why should it delude us into believing it is causally effective if it is really doing nothing? And how can we actually construct a purely mind-independent material dynamics that gives the same predictions as empirically successful processes, as the empirically successful combination of process 1 and 2 that brings our known to exist minds into the dynamics in a way that conforms to how it feels to behave as we do, and that is in harmony with the evidence of everyday experience? I mean, yeah. So another question that I have is that if you go with the classical mechanics explanation, with the mind having no function, but still convincing us that it exists without having a function, wouldn't a process to convince you that it exists or does anything require doing something in a way which wouldn't be doing nothing? So isn't it really inconceivable for it to be doing nothing? Because we know that our thoughts and mental efforts exist, and hence probably have an important function, it is not an irrational tour de force to try to show that they exist yet have no. Is it not an irrational tour de force to try to show that they exist yet have no causal power? Why should we try to evade using such a wonderful theory that is so well defined both mathematically and logically, and that works so well in practice, instead of trying to more fully exploit it? If one simply adds ad hoc to classical mechanics the postulate that certain brain activities produce or are the associated conscious thoughts, then a correlation between brain activities and consciousness is imposed by a fiat, having no logical roots in the classical physical theory, which is less logical. And if non-physicalist, if non-material explanations are considered unparsimonious to, well, physicalists or materialists, then the alternative that they propose effectively, it's a sort of deus ex machina sort of thing. It's like, it's not even that consciousness does it. It's like some unknown external force just does it. I mean, from that perspective, it could be a computer in a giant simulation, or it could even be just a theistic deity in the classical sense, which seems heavily implied by this, just imposed by fiat having no logical roots in the classical physical theory. At least, and yet, this is coming from a perspective that supposedly is against mentioning things that are dealing with the non-physical. And yet, for it to make sense, it requires something that has no logical basis, roots in classical theory at all, just some unknown thing, as to why or what conscious thoughts are. Now, I guess the only thing they've got really for this is that we don't know yet, which is pretty weak in terms of explanatory power, especially given that when you look at the Copenhagen interpretation taken as a realistic explanation of reality. You know, when you look at that and we look at how it actually fits the evidence better than the alternatives, especially even Bohmian mechanics and what was the other one we dealt with in the last episode? RQFT, which is a relativistic quantum field theory, which is like, it's very relative. So that one is like, so everything's relative, but there's no like, but it's still materialist. So I would say it's almost like the postmodern one, right? The sophist one. But that's just my take on it. Yeah, so that one fails. So basically, even if you abandon the even if you embrace relativism to the fullest extent, if you don't abandon the materialism, you can't really explain it. It just seems like random. Anyway. Where were we? It causes our consciously instigated probing actions to become postulated effects of physical brain actions, not their causes. Now keep in mind, postulated effects. This is just hypothetically saying we suggest that it's an effect of physical brain actions with no basis and nothing backing it up, no evidence, no logic or anything, just a postulation. To become postulated effects of physical brain actions, not their causes, as in quantum mechanics, and consequently reduces us to effectively thoughtless mechanical automata. So, I mean, it not just doesn't do that, it's just weaker theory. But why is this 17th century notion, which is so despised by many philosophers, and which is so contrary to our first-hand feeling of what we are, and is seemingly absurd and senseless, be such a compelling desiderata today, when it has been reversed by the superseding, highly successful contemporary quantum physics? This current theory recognizes our experience-based knowledge as both the proper foundation of science and also an essential part of the cause of process one, choice or probing action. Why should this reasonable, useful, and well-defined role specified by contemporary physics be rejected in favor of what seems a total absurdity about our minds proclaimed by a failed 17th century false start that makes our lives a farce? I didn't need to say it like that, but it really had a ring to it, and I did that. So, yeah, I mean, exactly though, it makes our lives a farce. So, yeah, I mean. Fair point, I guess. The quantum alternative is a mind-matter dualism in which our minds, by virtue of their capacity to freely choose probing questions combined with nature's born rule restricted reply, allow us to tend to actualize the bodily actions that we mentally intend. Our minds do matter in a way essential to our physical survival, well-being, and purpose. So I generally agree with that statement, that paragraph. Something that is different from my perspective there is they're talking about mind-matter dualism, where honestly my perspective is more like mind over matter, not mind alongside matter. The idea that the matter side of things is kind of an illusion created from the mind in the first place. Mentalism, or you could say objective idealism, or pantheism. Yeah, but you know, they're making a good point, and that's the end of the chapter. It's a pretty small chapter, so you know, I might as well get to the next one. Oh, this is interesting. Reality and spooky action at a distance. Ooh, yeah, that sounds particularly interesting. Let's just see how long this chapter is. Oh, yeah, that's pretty short too. Spooky action at a distance. Quantum mechanics has a peculiar feature that Einstein called spooky action at a distance, and which he found problematic. The problem arises under certain realizable empirical conditions involving two different experiments performed at essentially the same time in two far apart experimental regions. Under the specified empirical conditions, the computational rules of quantum mechanics assert that the psychophysical event initiated by the free choice of experiment made in one experimental region instantly changes the quantum state that controls the quantum predictions about outcomes appearing in the faraway region. The empirical validity of these predictions has been amply confirmed by experiments of a kind first performed in the early 1980s by French experimentalist Alain Aspect and his colleagues, and that are by now quite commonplace. Before we carry on here, I would add that if you've been following the Schopenhauer reading, the one about, it's not Decoding Schopenhauer's Metaphysics by Bernardo Castro. In the last episode, I think, I was actually talking about how this idea of, think like it's a light bulb and two observers, and there's in a tube, and there's an observer on the left, there's an observer on the right, and they're both looking at it, right? And I was saying, and it was saying basically, so the observers both see that, and there's a quantum interaction where what one person's state of mind, what in this sense would be process one person's mental choice or mental state of mind affects what happens, right? But the other person's affects what happens. And there's a sort of co-creation where what happens is kind of an a sort of composite of what both of them, their mental state and their perception. So in a sense, the process one of one person and process one of the other person each interact to bring about a result. So this could be translated in a sense to the law of attraction, where we affect the reality around us, but and this is a manifestation, this is a creation, but we co-create it with everyone else, right? And then there's the idea that, well, suppose if the tube is light years long on one side, but a whole bunch more light years on the other side, by the time one person sees it on the left, they'll see it before the other person, but there's still that quantum interaction that transcends time. And then I took one step further and was like, well, I mean, each star is a source of light, and every single observer of that light at every different point in time and space where they encounter it are all quantum connected via that light and being a source, so they're all quantum connected. And if you think about the idea of the Big Bang, which isn't necessarily guaranteed to have even happened, but suppose it did, then everyone's holistically connected in that sense. Anyway, I just brought it up because I do feel like it relates to this. Yeah, it felt right, so I did it. So yeah. The key phrase, free choice, means that the choice of which large-scale measurement procedure is performed in the region can be selected whimsically by the experimenter, or by a quantum random number generator, or by any other process that is effectively uncorrelated to the system being measured. The essential point is that the quantum prediction for what will be consciously perceived depends directly upon which experiment is set up and performed, but not upon the manner in which that experiment setup is chosen. The process of choosing the experiment is presumed to be dynamically independent of the system being probed by the experiments. This lack of dependence is generally agreed to mean that the choice that emerges from the process of choosing the experiment can be treated in the analysis of these experiments as a locally generated free variable. The quantum dynamical origin of spooky action. The spooky action arises within the quantum mechanical formalism from the fact that the quantum state of the entire physically described universe is defined at each instant of the advancing sequence of instants in time, or at a relativistic generalization of an instance in time, at which a collapse happens or occurs. This state represents an objective, collective state of the known physical state of affairs all over all of 3D space at that instant of time. If at some instant nature makes a choice of response to a probing action that is localized in some confined spatial region, then, according to the basic quantum rules, the quantum state of the universe changes, not just in that local region, but over all of the 3D space at that instant of time. This abrupt local change is what's called a collapse or a reduction of the quantum state. Einstein calls this global collapse spooky action at a distance, and believed that no such non-local action could be physically real. So I guess he interpreted it as a sort of something that came out of the maths that is like something unresolved, or almost like a mistake or something. So intriguing. And essentially, this is hard to deal with, but the classical paradigm or the physicalist and materialist paradigm, I mean, this is transcending of locality here. It's faster than light. In fact, it's instant across distances, as if every location in 3D space is adjacent in a dimensional sense that is more than 3D. And also, there's a sense of, if it's one place effect, if the state of observation in one place affects what happens everywhere, and every other place observations affect everything, then it's all a co-creation, right? That's what it suggests to me. And so, I mean, it's a global collapse. That's what Einstein described it as. No, it's a collapse of possibilities into one, but that is, in a sense, through process one, it's like a picking of what possibility will play out, and then it plays out. But lots of people do this. But one choice affects the whole universe. Now, I'll consider it, take a step back here and consider this spiritually. Not in terms of proving pantheism, just like generally. Our choices have a way more impact than we realize. There might be a reason why there's so much concern by extraterrestrial visitors and extraterrestrials across the universe as to what happens on Earth. Because maybe the consequences of what happens here are much wider than we think. But then again, the consequences of what happens everywhere are wider than we think. But still, that's significant, that's notable. Which explains why it's very soon after nuclear bomb testing was first done, the nuclear bombs was first used. It's very soon, it's immediately after World War II, basically, that the aliens are coming along like, just stop that now, right? Don't do that, it's wrong. They were really like, really insistent that it must not happen, that humanity is unite and stuff, or something. According to, I can't remember the name of the author right now, but Exopolitics, he wrote Exopolitics, the book called, that's the end of the book. Anyway, so I mean, there are being reports of people who are, what's it? Not dog whistle, what's it called? People revealing the truth that has been hidden in official files, you know, like that sort of thing. Now, yeah, I'm not going to get more into that UFO subject right now because this is not what we're talking about. Okay, so evasion via pragmatism. Theoretically explicit and essentially instantaneous actions at a distance occur in quantum mechanics by conjunction with the collapses/reductions of the quantum state. These collapses are essentially features of practical quantum mechanics. They are needed to keep the quantum state in line with our empirical knowledge. So that's the first thing. It's necessary. You can't even deny it, right? They are needed to keep the quantum, right? But the existence of such transfers of information conflicts with Einstein's theory of relativity, which limits the speed of motion of physical matter, and correspondingly, the speed of any transfer of information to the speed of light. The founders of quantum mechanics did not want to admit or suggest that, in defiance of the theory of relativity, information could really be transmitted faster than light. Hence, they evaded the problem by adhering to the pragmatic position that the physical state of affairs represented by the quantum state was not a representation of physical reality itself. For some reason, they didn't say why. I guess they're just like, it's just not a representation of physical reality itself, but something more akin to human knowledge than to classically conceived matter. Just cause, I guess. Being also unwilling to defend the idea that the physical state represents some absolute kind of knowledge, which would mean a retreat into idealism, deemed antithetical science, the founders adopted the evasive position that the quantum mechanical state was merely part of an invented practical human tool for making predictions about upcoming empirical findings. Thus, no claim was made that the quantum mechanical state represented reality. No claim was made about any real property of nature itself. You know, what you'd think science is about. Direct conflict with Einstein's ban on real faster than light transfer of information was thereby dodged. The EPR paper. The assumed absence of any real spooky action at a distance was the basis of an effort by Einstein to prove that a quantum mechanical description could not provide a complete description of physical reality. In 1935, he wrote, in collaboration with two young colleagues, Boris Podolsky and Nathan Rosen, one of the most renowned scientific papers of all time, entitled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" This paper is usually identified by the initials of the last names of its three authors, EPR. It assumes, in concordance with the theory of relativity, that information cannot be transferred faster than light, and then argues, on the basis of the predictions of quantum mechanics, that this theory cannot provide a complete description of the physical reality. But the authors opine that a complete and non-spooky theory of physical reality is possible. The thing is, it's based on assumption. Bohr's response to EPR. This is Niels Bohr. The easy response to EPR by the founders would simply have been to simply re-emphasize that quantum mechanics does not claim to describe physical reality itself. However, a simple response of that kind would have sparked among scientists who aspire to be more than high-level engineers efforts to find a more complete theory. Making such efforts is exactly what Einstein believed scientists interested in basic questions ought to be doing, but what the founders of quantum mechanics believed that potentially useful scientists ought not to be doing. Thus, Niels Bohr, the senior founder of quantum mechanics, chose to answer EPR by focusing on the slippery question of what constitutes physical reality. What exactly is physical reality? A logical sound argument pertaining to physical reality requires giving some definite meaning to that phrase. But our ideas about physical reality are deeply influenced by our experiences of the world around us, which seem to conform to the principles of classical physics. Thus, any proposed characterization of physical reality is in jeopardy of being challenged as resting on intuitive ideas alien to quantum precepts, and hence being prejudicial as begging the question. The EPR paper was built, therefore, not upon some notion of physical reality that could be attacked as obscure, unscientific, or question-begging. It rested instead on the demand, enshrined in Einstein's theory of relativity, that information cannot be transmitted faster than light. The opening for this demand was slipped into their famous criterion of physical reality. This criterion asserts that if, without any way of disturbing a system, we can predict with certainty, i.e. with a probability of unity, the value of a physical quantity, then there exists an element of physical reality corresponding to that quantity. I mean, I get it. It's very understandable. But just because you can predict the numbers of things, that doesn't mean why it's playing out that way is clear, and also it's without in any way disturbing a system. That is proven to become very difficult in quantum physics. But it's also suggesting that if there's any physical quantity that can be predicted, then physical reality exists, and thus that we can't say that, and thus that's just faster than the light thing, which means that you can't go faster than light, which means that any quantum theory that does suggest going faster than light can't be treated as actually true in that sense. Another issue is that if you think about it, this is dealing entirely with process 2, right? Which is things playing out according to the Schrodinger equation, right? Essentially. But it's not dealing with the mental free will aspect of things. It's just saying, looking at how it plays out without really accounting for the choice of which, by the observers, which possibilities play out. It's kind of treating it like, well, it's just randomly collapsing into one of them, rather than the mental state truly, and the state of nature, which kind of are kind of linked anyway, truly affecting what happens. Now, if I'm aware, it does seem to involve the Born rule as well. So yeah, it doesn't, it's clever what Einstein did here, but it is evasion. That's my take on it anyway. The requirement without in any way disturbing was met by considering situations in which the possible disturbance would require faster than light action. EPR were then apparently able to conclude that a certain pair of properties that were represented by non-commuting operators were both physically real and hence simultaneously definable, although the properties of quantum mechanics are unusable to encompass that possibility. Thus, the quantum mechanical description was proved to be incomplete. Of course, a simple alternative conclusion would be that faster than light actions can occur. Most of the EPR argument was straightforward physics and not open to challenge. But it depended upon one metaphysical element, the EPR criterion of physical reality, which begins with the words, if without in any way disturbing a system. Bohr attacked this metaphysical element of the EPR argument in a subtle way. Bohr states, of course there is in a case like that, just considering no question of a mechanical disturbance of the system under investigation during the last final last critical stage of the measuring procedure. But even at this stage, there was essentially a question of an influence on the very conditions which define the possible types of measurements regarding the future behavior of the system. Since these conditions constitute an inherent element of the description of any phenomena to which the term physical reality can be properly attached, we see that the argumentation of the mentioned authors does not justify their conclusion that the quantum mechanical description is essentially complete. So any conditions that you could call physical reality have mechanical disturbance of the system. Is that what he's saying? And therefore it doesn't justify the conclusions. All right, we'll see what it says in the book. Bohr argued, however, that quantum mechanics was pragmatically complete, which in the end is what matters most to most physicists, who could now, if challenged about the failure of science to talk about physical reality, refer to Bohr's reply to the EPR argument pertaining to that issue. Notice that EPR's argument is based on the matter-related assumption in physical reality that in physical reality, information cannot be transferred faster than the speed of light. Whereas Bohr's argument is based on the pragmatic idea that our understanding of nature should be based not on prejudicial assumptions about imagined to exist matter, but on our actual knowledge and on the possibilities of our future knowledge. So if the conflict comes down to a question of the proper foundation of science, is it the materialistic concepts of classical physics stemming from the postulates of Isaac Newton, or is it what we actually know or are able to know, as was urged by David Hume and other empiricists? In spite of this fundamental disagreement, the two protagonists did agree on one key point. There could be no real transfer of information over space-like intervals. But that presumption is proved wrong under the weak conditions of the proof given in Appendix 1. That proof rules out Einstein's classical matter-based conception of physical reality, but is completely compatible with the psychophysical conception of reality specified by von Neumann's orthodox formulation. There was no need to retreat from the idea that a rationally coherent, basic realistic physical theory, namely realistically construed orthodox quantum mechanics, can accommodate 1. The findings of the atomic physics, 2. The classical character of appearances, 3. The evidence for the causal effectiveness of our mental intentions, and 4. Spooky actions at a distance. So, I do want to see Appendix 1, because it might be helpful for you guys, gals, whatever, to clarity. Appendix 1. It's odd because it says Appendix A, B, C, and D. So, okay, let's have a look, see what comes up here. Suppose we'll get to it later. Suppose 1 and A. Oh, there's a whole bunch of stuff to talk about here that would probably have to be in a different chapter, to be fair. Or it could, I'm not sure what to do about this. So these appendices, I could just read it all in chronological order, this whole book, but it does seem relevant, that's the thing. You normally know what to do, but when they've got stuff like this in the book, it's a bit more, All right, so it's talking about Bael's theorem, and that's something we're about to get to. So, all right, so I won't go to that appendix. I'll just keep reading. Bael's theorem and the nature of reality. Historically, this controversy lay semi-dormant, with practicing physicists generally siding with the pragmatic position of Bohr until John Bael wrote a paper based on the notion of hidden variables. Bael's hidden variable approach added to the usual assumptions of the validity of the empirical predictions of quantum mechanics and the notion of effectively free choices on the part of the experimenters, and the further assumption that there is an underlying, invisible, hidden, physically described superstructure. Well, I keep saying things wrong. Physically described substructure that carries the causal connections. In exact analogy to classical statistical mechanics, each empirical situation is represented by a sum of statistically weighted, physically defined possible real states of the system being studied. Following Bael's lead, these quantum analogues of the physically defined possible real states of classical physics are labeled by the Greek letter lambda. Although I would say that each of these states could be deemed like different process twos, but yeah. This hidden variable quantum theory is applied in the context of the Bohm-Bell experimental situation, which involves two spin half particles existing initially in a certain, e.g. singlet, spin state. These two particles then fly apart in opposite directions for two far apart experimental regions in which a measurement is performed in each. These two far apart measurements are performed at essentially the same time in the common rest frames of the two experiments. The measuring device in each region also has two alternative possible settings. So altogether, there are 4 settings under consideration, and for each setting, 2 alternative possible outcomes. One of these alternative possible outcomes is labeled with an identifying label +1, and the alternative possible outcome of the same measuring process is labeled with a -1. I'm assuming here, for simplicity, perfect geometry and 100% efficient particle detectors, and shall stick to this idealized case. Each possible state, lambda, of the universe specifies which of the 2 alternative possible measurements is performed in each region. For each of these 2 possible measurements, which one of the 2 alternative possible outcomes of that measurement occurs. The choices of which measurements are performed in the 2 regions are treated as 2 free variables, and the no faster than light transfer of information condition, no FDL, is imposed by requiring the outcome of each region to be independent of which measurement is chosen and performed in the faraway region. Bael's analysis is based on a correlation function. This function specifies for each of the 4 considered pairs of settings that include 1 setting in each region, the degree of correlation between the labeled co-occurring outcomes in the 2 regions. This correlation function is a number that can vary from the value +1 if the labels of the co-occurring outcomes in the 2 regions always agree, to the value -1 if the label of the occurring outcome in the region is always opposite to the label of the co-occurring outcome in the other region. This function is defined for each pair of settings of the devices that has 1 setting in each of the 2 regions by averaging the product of the labels of the co-occurring outcomes in 2 different regions. Here, averaging the product of the labels means summing over the product of the 4 alternative possible combination of paired labels, dividing by 4 and weighting each pair with the quantum probability of that possible combination of the 2 far apart outcomes for the specified by lambda pair settings of the 2 devices. Now, I'm sorry if that was a bit heavy for you. It might have been a bit heavy for me as well. But basically, what I'm getting from this is the degree of interaction is measured by the averaged out distance between the 2 observed. So there's an observation made in one area and an opposite area. And the difference, there's a function, a mathematical function that measures the difference of the states based on averaging them out. And this is also done with the other two opposites because there's 4 states. I think that's what it's saying, more or less. I might be wrong. The key step of Bael and Associates is to invoke the demand for no faster than light transmission of information by converting for each fixed lambda the contributions of the correlation function into the product of 2 separate factors, each containing the dependence on both the choice of setting and the choice of outcome in just one of these 2 factors. Thus, no FDL is implemented by Bael by factoring the formula for the correlating function. But this factored form cannot be simultaneously valid for certain 4 alternative possible choices of the pair of settings in the 2 regions. Thus, implementing no FDL in this way leads to a contradiction. If this favored form were to be acceptable, then the hidden variable theory could, with some justification, be said to represent a certain local realism. That title, local realism, is the title that the proponents seem to prefer to local hidden variable theory, in conjunction with their claim that no local realistic theory can be compatible with the predictions of quantum mechanics. But that wording invites drawing certain logically unwarranted conclusions. The hidden variable theory can reasonably be called realistic. It is basically similar to classical statistical theory, which rests on the normal classical idea of real material worlds. If a certain locality condition is then imposed, the contradictions with the empirical data and quantum predictions ensue. Then it must seem that given a demand that the basic theory must describe reality, nature must be non-local, contrary to Einstein's demands. So this creates a problem. And this problem is essentially that you can have realism that is the opposite of idealism. So the idea you can abandon, okay, so you can have materialism or physicalism, but you can only maintain it at the price of doing away with the idea of locality, right? So that means you can have non-local materialism, right? You can have there being an objective physical reality that determines things, that being what determines things entirely, right? You can have that, but only in local situations through this method that was described. Or you can do away with, you can have locality, but not with realism, right? You can't have both. Now, this means that either way, it's something that Einstein was uncomfortable with. Okay? And also, the non-local thing is fundamentally, you could say, a faster than light thing, perhaps. Or at the very least, this non-locality, at the very least, to me, hints at pantheism, or at least has a commonality with it. However, there are other ways to achieve a realistic ontology. One of them might be able to evade the need for non-locality. Hence, FDL is not entailed merely by the need for it in the hidden variable model. All right, fair enough. Moreover, it has been well known since a 1984 paper of J. Jarrett that factorization is equivalent to the conjunction of parameter independence and outcome independence in the terminology of a chimney. So I assume they're doing factoring here, and I guess it's effectively equivalent to parameter independence and outcome independence. So the failure of the factorized formula to accommodate the quantum predictions and the empirical data entails either FDL transfer or outcome dependence. The dependence of the outcome in one region, which is outcome dependence, is the dependence of the outcome in one region on the outcome in another. And FTL transfer would be information, say in one mind, being transferred faster than light, effectively instantly, to another location. So the observer, an observer will observe something at one location, different location, something that a quantum dynamics is actually affected by that. So honestly, they seem pretty similar to me. The outcome of something is dependent on something in a different location, that idea. There's something FTL about that, isn't there? Or to something about the nature of reality being there interconnected, which actually seems to make more sense to me. But you can still kind of say that's FTL, but whatever. But outcome dependence is the normal feature of empirical predictions in the situations under consideration here. Hence, one cannot conclude from the failure of factorization that there must be FTL transfer of information. The failure of outcome independence suffices to account for the failure of factorization. An actual proof that there must, under appropriate conditions, be FTL transfer of information is given in Appendix 1. It achieves what the hidden variable approach may seem to claim to achieve, namely the need for FTL transfer of information about the experimenter free choices, but does not logically achieve it. So it does what is not logically achieved by hidden variable theory. And I guess we'll get to that in Appendix 1. I suppose I could skip to Appendix 1, but I'm a bit confused because in this text, like, it doesn't say Appendix 1 as far as I can see. It says Appendix A. I assume they correlate, but I don't know. Okay, it does mention Bell's theorem, so I will go see if I can find it here. Okay. How long is this anyway? How many pages is this appendix? Yeah, I can do Appendix A or 1. Proof that information must sometimes be transferred faster than light. Strengthening Bell's theorem by removing the hidden variable assumption. In the context of correlation experiments involving pairs of experiments performed at essentially the same time in a very far apart experimental regions, Einstein famously said, "But on one supposition, we should, in my opinion, hold absolutely fast. The real factual situation of the system S2 is independent of what is done in system S1, which is spatially separated from the former." Understandable, that realism, but that's not backed up with the science. This demand is incompatible with the basic idea of standard Copenhagen Orthodox Quantum Mechanics, which makes 2 relevant claims. 1, experimenters in the 2 labs make local free choices that determine which experiments will be performed in their respective labs. These choices are free in the sense of not being predetermined by the prior history of the physically described aspects of the universe, and they are localized in the sense that the physical effects of these free choices are inserted into physically described aspects of the universe only within the laboratory and during the time interval in which the associated experiment is being performed. 2, these choices of what is done with the system, being measured in one lab can, due to a measurement-induced global collapse of the quantum state, influence the outcome of the experiment performed at very close to the same time in the very far away lab. So spooky actually distance, right? This influence of what is done with the system being measured in one region upon the outcome appearing at very nearly the same time in a very far away lab was called spooky extra distance by Einstein and was rejected by him as a possible feature of reality. John Bael's quasi-classical statistical theory. Responding to the seeming existence of the quantum world of spooky actions, John Bael proposed a possible alternative to the standard approach that might conceivably be able to reconcile quantum spookiness with reality, in inverted commas. This alternative approach rests on the fact that quantum mechanics is a statistical theory. We already have in physics a statistical theory called classical statistical mechanics. In that theory, the statistical state of a system is expressed as a sum of terms, each which is a possible real physical state of the system multiplied by a probability factor. So, yeah, he was trying to salvage materialism, I suppose. Bael conjectured that quantum mechanics, being a statistical theory, might have the same kind of structure. Well, conjectured. Such a structure would satisfy the desired properties of locality and reality, local realism, if each real physical state in this sum, the relationships between the chosen measurements in the two regions and the appearing outcomes are expressed as the product of two factors, with each factor depending upon the measurement and outcome in just one of the two regions. The question is then whether the statistical properties of such statistical ensemble can be consistent with the statistical predictions of quantum mechanics. Bael and his associates proved the answer is no. They considered, for example, the empirical situation that physicists describe by saying that two spin half particles are created by the so-called spin singlet state, and then transferred to the two far apart but nearly simultaneous experimental regions. The experimenter in each region freely chooses and performs one of the two possible experiments available to him. Bael et al. Then proved that the predictions of quantum mechanics cannot be satisfied if the base states satisfy the factorization property demand of local realism. A theory satisfying this demand is called a local hidden variable theory because the asserted underlying reality is described by variables that cannot be directly apprehended. They're mysterious, right? But we don't know that. We haven't got that to deal with. Now, I can understand dealing with something that doesn't have evidence. I mean, like, I'm into spirituality, right? But I'm not doing science. I mean, I'm referring to it here, which is arguably convenient for me. Given the methodology they're using here, it is to meet that if that's what they're doing, right? Otherwise, it's not science. So, I guess I'll carry on. Two problems with Bael's theorems. Bael-type theorems, if considered as proofs of the logical need for spooky action, Bael-type theorems, if considered as proofs of the logical need for spooky actions in a theory that entails the predictions of quantum mechanics, have two problems. The first is that the theorems postulate a reality structure basically identical to that of classical statistical mechanics. Bael's theorems then show that imposing locality factorization for each fixed, that's a Greek symbol, I don't know what it is. It's like an upside down Y. Within this classical type reality structure is incompatible with some predictions of quantum mechanics. But that result can be regarded as merely added confirmation of the fact that quantum mechanics is logically incompatible with the conceptual structure of classical mechanics. Simply shifting to a classically conceived statistical level does not eliminate the essential conceptual dependence on the known to be false concepts of classical physics. Now, and does it really seem fitting with the advances in physics at the time and that have been happening through quantum physics to then just say, well, let's just go back to a statistical formulation that's basically based on prior to quantum physics? It's like, you know, there's the on the shoulders of giants principle. Ironically, this is something that Newton mentioned, that he's standing on the shoulders of giants. It's like going back a step and getting off the shoulders of one of them or something. Do you know what I mean? Like, so you've got these advances in quantum mechanics. We're like, let's not use that quantum stuff. Let's just go with an old, like the old approach, and try to use that to avoid the implications of quantum mechanics. That's rationalization, right? That's evasion as well. Simply shifting to a classically conceived statistical level does not eliminate the essential conceptual dependence on the known to be false concepts of classical physics. There we go. The second problem is that the condition of local realism is implemented by a factorization property described above that goes far beyond Einstein's demand for no spookiness. So there we go. The whole point of it is to avoid that. And in order to maintain it, the materialism, all you can do is reduce the amount of spookiness. I mean, it sounds like a losing battle there. In addition to the non-dependence, and also it kind of renders the whole thing pointless. So like, why not just accept it at that point? Why not accept the spookiness at that point? I mean, like, if it's spooky anyway, the whole reason for avoiding spookiness or reducing it, it's just like gone. So at that point, it's just like not as scientific. That's what I think anyway. In addition to non-dependence of outcomes in a region upon what is done, in the faraway region, local realism entails what Shimoni calls outcome independence. That condition goes significantly beyond what Einstein demanded, which is merely a non-dependence of the factual reality, occurring outcome. If in one region on the choice of which is merely not a non-dependence of the factual reality in one region on the choice of experiment performed in the faraway region. Outcome independence demands that the outcome in each region is independent also of the outcome in the other region. That property, outcome independence, is not something that one wants to postulate if a resulting incompatibility with predictions of quantum mechanics is supposed to entail the existence of spooky actions at a distance. The unwanted independence assumption is not just a minor fine point. Consider the simple example of two billiard balls, one black, one white, shot out in two opposite directions in two far apart labs. The physical example allows, given the initial symmetrical physical state, the outcome in one region to be correlated with the outcome appearing in the other region, without any hint of any spooky action at a distance. A black ball in one region entails a white ball in the other, and vice versa, without any spooky action. Hence, Bael's theorems do not address or claim to address the key question of compatibility of Einstein's demand for no spookiness with the predictions of relativistic quantum mechanics. Bael's theorems are based on the stronger assumption of local hidden variables. Bael's theorems, regarded as proofs for the need for spooky actions, are thus deficient in two ways. They bring in from classical statistical mechanics an alien to quantum mechanics idea of reality, and then assume in the process of proving a contradiction, a certain property of outcome independence that could lead to a violation of quantum predictions without entailing the lack of spookiness that Einstein demanded. I will add, all for the sake of the lack of spookiness that he demanded. So it kind of fails in its purpose there. The question thus arises whether the need for spooky actions can be proved simply from the validity of some empirically well-validated predictions of standard quantum mechanics, without introducing Bael's essentially classical hidden variables. The answer is yes, there is a way to do that. So, the proof. The following proof of the need for spooky actions places no conditions at all on the underlying process of reality. Places no conditions at all on the underlying... Oh, I said it wrong again. Okay. The following proof of the need for spooky actions places no conditions at all on any underlying process or reality beyond the macroscopic predictions of quantum mechanics. It deals exclusively with connections between macroscopic measurable properties. This change is achieved by taking Bael's parameter, upside down y, to label now the different experiments in a very large set of simultaneously performed similar experiments, rather than the different possible basic microscopic states, upside down y, of statistical ensembles. The ontology thereby becomes essentially different. Okay, so I'm going to try to actually take in like what I just read here. So, so the change achieved by taking Bael's parameter in a different set of simultaneously performed experiments. Rather than different possible basic microscopic states of statistical ensembles. So basically it's two different things, and so they're not related. I'm not sure. The ontology thereby becomes essentially different, though the mathematics is similar. The macroscopic experimental arrangements are the ones already described above. In the design of this experiment, the physicists are imagining that a certain initial macroscopic preparation procedure will produce a pair of tiny invisible spin-half particles in what is called the singlet state. These two particles are imagined to fly out in the opposite directions to two far-away experimental regions. Each of these experimental regions contains a Stern-Gerlach device that has a directly preferred axis that is perpendicular to the incoming beam. Two detection devices are placed to detect particles deflected either along this preferred axis or in the opposite direction. Each of these two devices will produce a visible signal or an auditory click if the imagined invisible particle reaches it. The location of the individual detector is specified by a given angle of the directed preferred axis, such as, okay, I'll show you this simple. It's like a circle with a line going down the middle of the directed preferred axis, such that a displacement along that particular direction locates the detector. Clearly, the two detectors in the same experimental region will then be specified by two angles that differ by 180 degrees. For example, if one detector is displaced up, inverted commas, then the other is displaced down. The angle something equals 0, whatever the symbol is, labels in both regions a common deflection to the right, e.g. along the positive x-axis in the usual xy plane. Under these macroscopic experimental conditions, quantum theory predicts that if the detours are 100% efficient, and if moreover the geometry is perfectly arranged, then for each created pair of particles which are moving in opposite directions to the two different regions, exactly one of the two detectors in each region will produce a signal, i.e. fire. The key prediction of quantum theory for this experimental setup is that the fraction f of the particle pairs for which the detectors that fire in the first and second regions are located at two different angles, given by a certain formula. Paraphrasing here. In the experiment under consideration, there are two alternative possible experiments in the left-hand lab. and 2 alternative possible experiments in the right-hand lab, making 2 times 2 equals 4 alternative possible pairs of experiments. For each single experiment on one side, there are 2 detectors, and hence 2 angles. There are altogether 4 times 2 times 2 equals 16 Fs. So that's fractions. Those are fractions, okay. I take the large set of these related angles, right? I guess? No. Okay, whatever. I take the large set of similar experiments to have 1,000 experiments. Then the fractions f of 1,000 are entered into the 16 associated boxes of the following diagram. Okay, so they do it 1,000 times, which multiplies the whole thing, and then they put it into a chart. And that way they can sort of chart the statistical results, I guess. Or probabilities, that is. Yeah, not statistics, it's probabilities. In figure A1, the first and second rows correspond to the 2 detectors. Okay, I'll show you that figure, all right? I don't know if you can make anything out of it really, but yeah, there it is. If you're watching, that is. I'm not sure about describing it even. It's got like 16 squares and different numbers on it and different notations. So it's a bit heavy, this bit, but I do feel like maybe you guys can get something out of it. Actually, how long is, oh, there's a whole bunch more. How long am I going to go on this? It's actually a whole bunch more pages, and this would be quite a long episode if we do all of them. I mean, if you've been listening to this section of this episode, thank you, I guess, because it's a bit heavy going, isn't it? So this is very mathematical here. And it's supposed to be a proof, but if I'm not actually dealing with the mathematics of the proof, there's not really a point me going over it. And that's the problem with what I've been doing here. But there's still interesting things said here. Okay. I'll skip a section and I'll say, I've listed these particular predictions because they are assumed to be valid in the following proof of the need for near instantaneous transfer of information between the 2 far apart but nearby simultaneous experimental space-time regions. These particular predictions have been massively confirmed empirically. The second assumption is localized free choices. The point here is that physical theories make predictions about experiments performed by experimenters with devices that detect or measure properties of the systems whose properties are being probed by these devices. The theory entails that the various settings of the devices will correspond to probe-associated properties of the system being probed. Of course, in an actual situation, these specified parts of the experimental setup are all parts of a universe that includes also the experimenter and whatever the experimenter uses to actually fix the experimental settings. Such a choosing part of the universe could, however, conceivably causally affect not only the setting of the associated measuring device, but say, via the distant past, also other aspects of the experiment. Because in the past, a whole set of causally things were done, decisions were done, which led to the experiment being set up and the lab being set up, even things relating to the lab being built and how it was built. So fundamentally, it's all connected, right? So that's what it means via the distant past. And it's conceivable, but if you think about it, I would add that it's inevitable and unavoidable. That's what I'm saying though, not the book. Those unsuspected linkages via the past could then be responsible for systematic correlations between the empirical conditions in the 2 regions. Correlations that are empirically dependent on which experiments are chosen and performed, but are empirically independent of how the experimental setups are chosen. In In view of the limitless number of ways that one could arrange to have the experimental setup specified, and the empirically verified fact that the predictions are found to be valid independently of how the setup is chosen, it is reasonable to assume that the choices of the experimental setups can be arranged so that they are not systematically connected to the specified empirical aspects of the experiment except via these choices of the experimental setup. This is the assumption of localized free choices. It is needed to rule out the remote possibility that the choice of the setup is significantly and systematically entering the dynamics in some other way than just the localized fixing of the experimental setup. Suppose then that we have two far apart experimental regions, and in each region an experimenter who can freely choose one or the other of two alternative possible experimental setups. Suppose we have in a certain region called source region a certain mechanical procedure to which we give the name creation of n individual experimental instances, where n is a large number, say 1,000. At an appropriate later time, the experimenters in the two regions make and implement their local free choices pertaining to which of the two alternative possible experiments will be set up in their respective experimental regions. At a slightly later time, each of these two experimenters looks and sees in each of the n individual instances which of his two detection devices has fired, and then records the angle X that labels that detector, thereby recording the outcome that occurs in that individual instance. So kind of repeats itself, but and this of course is done 1,000 times. And the whole thing is displayed into 16 boxes based on 16 different possibilities. And how much that comes up in each is represented probabilistically. And the details of that I'm not really going to go into because you don't really want that, do you? And I'm not sure if you'd understand it if I did, to be honest, because I just don't know maths myself, let alone assuming that the listener. The fluctuations become relatively smaller and smaller as n gets larger and larger. So I will, for simplicity, ignore them in this discussion and treat the predictions to be exactly ready for n equals 1,000. The two experimental regions are arranged to be essentially simultaneous, very far apart and very tiny relative to their separation. These two regions will be called the left and right regions. No essentially instantaneous transfer of information about localized free choices assumption made here is that no matter which experiment is performed in the region, the outcome appearing there is independent of which experiment is freely chosen and performed in the faraway region. This means, for example, that the experiment on the right is changed from the case represented by the far left two columns. Okay, too much reference to the actual chart here. Yeah, again, it's getting to the point where I'm going into loads of details, and it just kind of, I want to get to conclusions here because otherwise it's just getting stuck in the maths. But of course, this is a proof, right? So okay, repeating the argument but reversing the order in which the two reversals are made, we conclude from exactly the same line of reasoning that box C can contain no more than 250 of the 500 integers box A. Thus, the conditions set on C that arise from the two different possible orderings of the two reversals are contradictory. I can tell you there's a contradiction, but because I didn't read the bits, the whole section of text before it, I don't know what that is. So, all right. Maybe I shouldn't have read that paragraph, but okay. We're getting close to the end of this appendix. Anyway. A contradiction is thus established between the consequences of the two alternative possible ways of ordering these two reversals of a localized free choices. The reversals being related to which way it goes and the two possibilities, I guess. Or, well, four. Because due to the locality hypothesis being examined, no information about the choice made in either region is present in the other region. No information pertaining to the order in which the two experiments are performed is available in either region. Hence, nothing pertaining to the outcomes can depend on the relative ordering of these two space-like separated reversals of the two choices. This argument uses only macroscopic predictions of quantum mechanics, without any conditions or mention of any microstructure from whence these macroscopic properties come. To demonstrate the logical inconsistency of combining a certain 16 empirically validated predictions of quantum mechanics with the locality hypothesis, that for each of these two high experimental regions, there was no faster than light transfer to the second region of information about macroscopically localized free choices made in the first. You know, I think what they're saying is it's actually a reductio ad absurdum argument. Now, a reductio ad absurdum argument is basically you take something to its logical conclusion and show that logically that conclusion is actually absurd, that it makes no sense, that it's contradictory, right? That it's absurd. And that's a reductio ad absurdum. And by doing that, you prove something wrong using itself. And that seems to be what they're doing here. So saying, in this setup, it actually creates a contradiction. And thus, it proves that certain thing can't be done, or at least that the hidden variable approach, a localized hidden variable approach, can't be done. It just doesn't work. The Bael's theorem proofs are rightly identified as proofs of the incompatibility of local realism with predictions of quantum mechanics, but local realism brings in both alien to quantum theory classical concepts and also an outcome independence condition, whose inclusion nullifies those theorems as possible proofs of the need for spooky action at a distance. Both of these features are avoided in the present proof. Which I guess you're just going to have to believe, because I didn't go through the details there. As regards Einstein's reality condition, namely that the non-spooky action condition pertains to the real factual situation, one must, but of course, use the quantum conception of the real factual situation, not an invalid classical concept. So that is not going to be a realist conception of the real factual situation. What it is going to be is something more like the Copenhagen interpretation, or maybe preferably realistically interpreted quantum physics. In ontologically construed orthodox quantum mechanics, in contemporary relativistic quantum field theory version 1 that I use, the version that I use, so I guess that's his, in the contemporary relativistic quantum field, right, okay. The real factual situation evolves in a way that depends on the experimenter's free choices and nature's responses to those choices. The no spooky action condition is a condition on these choice-dependent real factual situations, namely outcomes observed under the chosen conditions. that is inconsistent with certain basic predictions of the theory. That is what that's what has just been proved. In classical mechanics, there are no analogous free choices. The physical past alone uniquely determines the physical present of the future. That's how it is in classical mechanics, but this has been proved that it doesn't work that way. It can't be explained in that way. The Einstein idea of no spooky actions involves comparing two or more situations, only one of which can actually occur. This is the kind of condition that occurs in modal logic considerations involving counterfactuals. But here, in the modal aspect, does not bring in any of the subtleties or uncertainties that plague general modal logic. For in our case, a specified condition on completely well-defined and unambiguous trial mathematical assumption of the non-dependence of nearby outcome upon a faraway free choice between two alternative possible probing actions. The proof does not get entangled with the subtle issues that arise with general modal logic. Everything is just as well defined as in ordinary logic. In this proof, there is no assumption of a hidden variable of an essentially classical kind lying behind the ontologically construed orthodox quantum theory. The phenomena here are rationally understandable in terms of the evolving quantum state of the universe that represents potentialities for experience that evolve via a Schrödinger-like equation punctuated by an ordered sequence of psychophysical events, each of which is an observer's personal experience, accompanied by a collapse of the quantum state of the universe that brings the evolving state into conformity with the observer-initiated experience of that observer. So each observer affecting the reality, all of reality, through the observations, interacting with all the other observers across a universe that has a holistic whole of co-creation. So panpsychism. The bottom line is that given the validity of some basic macroscopic predictions of quantum mechanics, there is no way that the macroscopic phenomena can conform to the predictions of quantum mechanics without allowing violations of the general notion that the information about local free choices cannot get essentially instantaneously to faraway regions and affect outcomes appearing in those regions. Wait, what's it saying? So the idea of not having faster than the light movement of information. That being violated by the predictions of quantum mechanics, in fact, the evidence of it as well, is unavoidable. It basically proves that Einstein, in this episode, what we have established is that essentially Einstein's requirement that no spooky action at a distance happens in reality, that reality doesn't involve that there's no spooky action at a distance, and that reality is realist. Basically, both of these are false. And that's what's been established, I would say. Well, and if not in this episode, certainly in what's been done so far. In the episode so far. It's basically, the case is being made increasingly solidly here. And there's no real avoiding it. Yeah, again, I am sorry that I went into such detail, just reading out like maths and stuff that even I don't really get, and it was kind of unnecessary. So I could have potentially done this episode a bit better in that sense, but I'm not perfect, and I'm fine with being, a podcast who's improving over time. Yeah, but essentially this really brings into question the materialist paradigm here, I guess, and Einstein's. So there's no real reason or justification for the continued focus on just being pragmatic about it, the predictions of quantum mechanics, and not treating it as an accurate description of reality, because the whole purpose of being pragmatic about it, which is avoiding violating Einstein's rule here that he set up, is that, well, it fails at doing that anyway, and it's proven that it doesn't work, and that it makes more sense not to do it. So there is no reason to do that. There's no reason to just treat it pragmatically at all. It's unscientific to do that. Right? That's what this proves. That treating it as an actual description of reality is the scientific way to go about it. And generally, that's what science is about, isn't it? Actually explaining reality. Otherwise, why do science? In fact, and when it comes to people who are advocates of science or defenders of science, generally the biggest thing they argue, and it's in favor of it, is, well, we can actually understand how reality is in a rigorous way that isn't based on just people making other assumptions. It actually allows us to have a good understanding of reality. And it's useful for stuff like, well, actual technology improvements and stuff. And understanding reality, like, it's a means for that. And if you're just abandoning the whole raison d'etre of science just to maintain materialism, you're being unscientific. And that's the issue here. So hopefully, while I won't go into like the ins and outs of maths so much, and I don't think I'll have to so much, but I'm not going to do it so much in this in future readings. But what we've got to is chapter 7, backwards in time, causation. Now that is going to be interesting. And just an idea what it might entail. What I mentioned about that light going in a tube in two different directions, and if one tube is way longer than the other, the observers at different points of time, or if that's a star, the observers at different points of time will affect what happens at different points of time, right? So observation affects different points in time and space. It's all, and since time is all like kind of an illusion, and all time and space is just like one anyway, makes sense. So yeah, I hope you enjoyed it, especially the and I hope you didn't find it unpleasant when I went into all that mathematical notation I didn't really get. But yeah, so I never really know what to say other than bye for now.